Okay, today's topic is going to be the measures of position and outliers. Things you're going to want to learn from this video is how to find a standard score, how to find percentile using the empirical rule, how to create a box and whisker plot using 5-number summary, how to calculate outliers, and how to find a percentile. So there are two standard scores. There is one standard score for a sample, and then there's one standard score for a population. They're both calculated the same way. However, the sample z-score or standard score has this strange little X in its formula. Let me grab my pen. So right there, that has an X in it. That is just the sample mean. And over here you have this funny little U. It's a Greek letter. That is the population mean. In the denominator of our formula, we have an S. That is the standard deviation for a sample. And this is just the standard deviation for the population. So they're both calculated the same way, they just use different symbols to denote that they're different in that one's a sample and one's a population. And again, just for a reminder, a sample is a random sample from the entire group that you're studying, or set of things. That's usually what we're looking at as a sample when we're looking at statistics. Statistics actually are the things that describe a sample, and we usually have a sample because it's really impractical to get the entire population. It costs a lot of money, it's hard to do for various reasons, and so we're usually looking at a sample and talking about statistics. Parameters are what describe a population. Okay. So that's how we calculate a standard score. And now you have probably heard of test scores following a normal or a bell curve, and in the middle here, this would be our mean right here. This would be the mean. And in a normal distribution or a bell curve, the mean is equal to the mode. So our mean equals the mode equals the median. Okay, that's true of a bell curve. And another thing that's true is between here and here, this is where this curve changes shape a little bit. We have the mean plus 1 standard deviation and the mean minus 1 standard deviation. And in that space, 68% of our values will fall. So 68% means that there'll be 34 between the middle and here, and another 34 roughly between the middle and the 1 standard deviation above. So another property of the normal curve or the bell curve is that within 2 standard deviations, we have 95% of our data. So that means that about 13.5% is between 1 and 2 standard deviations here, and another 13.5 below here between -1 and -2 standard deviations. If I were to add up all three of these regions, I'd end up with 95% or 0.95. And that leaves me, and you'll probably have heard the saying that anything outside of 2 standard deviations is normal and anything outside of that is unusual. So usual is within 2 standard deviations of the mean. And unusual is anything greater than 2 standard deviations from the mean, away from the mean. So that leaves just 2.5% on each end, so 0.025 of our values would be between 2 and 3 standard deviations above, and 2.5% would be between 2 and 3 standard deviations below. And all of that adds up to 1. So to put this into some kind of context that you can relate to, if the students in Math 240 class have a mean score of 81 and a standard deviation of 4 on their first exam, what scores would be necessary to score in the top 2.5%? The first thing you'd want to do is I want to fill out this normal curve with values so that you have an idea of what this really means. Our mean is 81 and a standard deviation is 4. So the mean goes right in the middle here. That's where most of the values are, and our score would be 81. 1 standard deviation above is here, and that is an additional 4 points. So 81 and 4 is going to give me a score of 85. 2 standard deviations above is 4 additional points. So that's going to be 89, a score of 89. And then 3 would be 4 more, and that would be a score of 93. And then 1 standard deviation below would be 81 minus 4, because I'm 4 points below 81. That's a score of 77. 2 standard deviations would be 77 minus another 4, which would be a score of 73. And then finally, 3 standard deviations below would be a score of 69. So that would be 3 standard deviations below. All right, 2.5% of my area is anything greater than 2 standard deviations above. So I would need a score of 89 or better to score in the top 2.5%. So quartiles are when you divide your data into fourths or into quarters. So we're going to use those same test scores we had before of the 10 students in a mathematics class. And if I want to find I'm going to break this into quarters. So first I'm going to break it into half. You'll note that I have 5 pieces of data on the left here and 5 on the right. And then if I want to break it into half again, I'm going to have to go here, right through that, and right through this. That's why my quarter 2, it's between 2 values. That's why I took the average for my median. Median and quarter 2 are the same thing. And you'll recall that that was 77.5. So here's quarter 1, here's quarter 2, and then here's quarter 3. Quarter 1 is 70, and quarter 3 is 85. So if I have an odd number of data points, it's going to be one of the values. If I have an even number, I have to cut them in half and take the average. So the interquartile range is Q3 minus Q1. In this case, it's 85 minus 70. And that gives me a value of 15. Things that we do with quartiles is it gives us we make box and whisker plots with it, and it gives us a way to get a visual of our data to see if our data is symmetric or not. And so our 5-number summary consists of the min, the quarter 1, our median or quarter 2, quarter 3, and our max. So our high, our quarter 1, our middle value, quarter 3, and our maximum value. In this case, it was 60, 70, 77.5, 85, and 90. And if I were to make a box and whisker plot out of this, I would need those values. So the first thing you want to do is have a good axis. You want to have an accurate axis, or your box and whisker plot is absolutely useless. Let's see if it's big enough. 60, 65, 70, 75, 80. I need to go as low as my lowest value and at least as high as my highest value. Okay, it's a little longer, but that's okay. So if I look, I want the interquartile range. I'm going to put a box around my interquartile range, and that goes from 70 to 85. That's where the box goes. Down the middle of that is, well, it could be in the middle, but in this case it is. It doesn't have to be. But is 77.5, that's my median. I put a line in the right where that belongs. And then the whiskers extend out to my min and my max. So 60 is my min, 90 is my max. And you can see that I'm a little closer, my box is a little closer to 90. Looks like somebody took my end over here and stretched it out. That means that it's skewed in that direction just a little bit. I have some low value that's pulling the data in this direction unnaturally. So I want to see if I have any outliers, and the formula for finding out if I have outliers is I need the interquartile range for that. So I could have values that are too high, and that would be, so I need an upper fence to weed those out. And I could have values that are unusually or too low, unusually low, and so I need a lower fence to check for those. And things that cause outliers most often is like a mistake or just some freak of nature, but usually it's a mistake. You have to decide that in the context of a situation. So my interquartile range is going to be, for the upper fence, is Q3. Oh, sorry, that's the interquartile range. I just messed up. Hold on. The upper fence is Q3 plus 1.5 times my interquartile range. Sounds complicated, but it's not really. My Q3 is 85 plus 1.5 times my interquartile range. We already calculated that to be 15. So I get a value of 107. I do not have any scores above 107, so that means I don't have any outliers that are too high. So to find the lower fence, it's Q1 minus 1.5 times the interquartile range. And that would be 70 minus 1.5 times 15, which gives me a value of 47.5. I don't have any values lower than that, and so I don't have any lower value outliers either. Okay, so percentile is the percentage of scores that are at or below the score that, or the data point that you're looking at. So percentage of scores in your data set or in your distribution at or below that value. So the 15th percentile, so for that I need to know how many data points I have. And I'm going to go back to the example with the test scores where we had 10 pieces of data. If I wanted to find the 15th percentile, I would take 15%, or in decimal, not percent, 0.15 times my 10 data points, which would give me a value of 1.5. That means that my 15th percentile is between the first and second value. And the first value was 60, my second value was 70, so I have to take the average of those. And if I scored a 65 on the test, I would be at the 15th percentile. Now the 90th percentile is going to be 0.9 times 10. That's going to give me the data point I want, which gives me 9. The 9th data point is 90. So a 90 is what I'd need to get to score in the 90th percentile. Finally, we're going to calculate the standard score for someone who gets a 60. You're going to have to refer to your notes from the first section for this. From the first section, we had a mean of from section 3.1, we had a mean of 77, and we had calculated a standard deviation of 9.78 for that data set. So the standard score is going to be our value, our x value, 60. Let me write that formula down again. It's x minus the mean divided by the standard deviation. So 60 minus 77 divided by 9.78 gives me a standard score of negative 1.74. That means that 60 is 1.74 standard deviations below the mean. Okay, and now if I want to calculate the standard score for someone who gets an 85, 85 is my x value. I still have the same mean, so it's 77 and same standard deviation, 9.78. When I calculate that, I get a positive value because 85 is above 77, so I should get a positive z-score. I get 0.82. I'm almost one standard deviation above the mean, but not quite. Okay, that's it for today.